Welcome to CSAI Think Tinker Learn. I'm thrilled to kick off our brand new series on system design. Before we tear into the networking layer, please take a moment to hit that like button, share this video with your fellow engineers, and subscribe so you don't miss a single deep dive. For those who want to follow along with the text-based version of these lessons, head over to our companion sites. It's on the GitHub pages, the link up in the description. The series is designed to give you a high-level architectural overview of our complex topics to keep things concise, digestible, and within 10-15 minutes. However, if there is a specific concept like Anycast or a BGP that you want us to drill down into a long-form video, dedicated video, just let us know in the comments below. Today, we are mastering DNS resolution, the exploded architecture. Let's get started. To understand why modern DNS is so complex, we have to look at why centralization fails. In 1982, the entire ARPANET relied on a single file called host.txt, which is still found in most of the Windows machine today, maintained manually by the Stanford Research Institute. Whenever a new computer joined the network, you had to update that one file. Today, we have over 350 million registered domains, and IP change every second due to CDNs and load balancing. A centralized directory is now a mathematical impossibility. As the red warning states here, centralized systems are a catastrophic single point of failure. If that one file or server goes down, the entire internet disappears. This realization led to the distributed hierarchical system we use today. This is the delegation tree. Instead of one server knowing everything, authority flows strictly downward. Think of it like a corporate hierarchy. The root consists of 13 logical nodes that don't know where example.com is, but they know exactly who is in charge of the .com, top level domain. The TLD then delegates to the authoritative name server, which holds the ground truth, the IP address. The mentor node here is the key to extraordinary design. No single node needs to know everything. They only need to know who to ask next. This allows the system to scale infinitely. How does the query actually happen? We use two types of logic, recursive and iterative. Your computer, the client, sends a recursive query to the resolver, usually provided by your ISP or Google. You're essentially saying, find the final answer for me. I don't care how you do it. The resolver then does the heavy lifting, performing iterative queries to the root, TLD, and the authoritative servers. It asks, give me a referral to the next server. The goal is to do all of this in under 100 milliseconds. Remember, clients never do the iterative work. The resolver acts as a shield, protecting the client from the complexity of the hierarchy. If the resolver had to go to the root server for every single click, the internet would crawl. This is why we have the memory stack. DNS records are cached at the browser, OS, and at the resolver level. Every record has a time to live, or TTL. A high TTL like 24 hours reduces network load but makes it impossible to change your IP quickly. A low TTL like 60 seconds allows for instant updates but increases latency. Here's a pro tip for your next migration. If you're moving servers, lower your TTL to 60 seconds, at least 48 hours in advance. If you don't, some users will be stuck hitting your old stale IP along after you have shut it down. Authoritative servers don't just return IPs, they manage a payload matrix of zone files. We categorize these by intent. For routing, we have A records for IPv4 and AAAA for IPv6. For delegation, we use NS records to point to other servers and MX for mail. For info and security, we use TXT and SOA. Note that AAAA, that is 4A, exists purely as a bridge during our long-term transition to IPv6. Each of these records serves as a distinct architectural purpose, ensuring that DNS is more than a phone book. It's a multi-purpose routing database. Now, for the classic interview trap, CNAME at the zone apex. According to RFC 1034, the zone apex, the root domain like example.com, must contain SOA and NS record. However, the DNS spec says that if a CNAME exists, no other record can exist for that name. This creates a mathematical collision. You can't have a CNAME and your mandatory SOA/NS record at the same time. This is why you often see example.com as a CNAME, but never the naked example.com. To solve this, modern providers use proprietary alias or ANAME records that flatten the response at the edge, providing the benefits of a CNAME without breaking the rules. DNS is actually a primitive layer 7 router. We use it for global traffic management, the round robin. The DNS server rotates through multiple IP addresses to distribute load. However, round robin is blind to server health. GeoDNS is much smarter. It resolves different IPs based on where the user is located. If you're in London, you get the Frankfurt Edge server. If you're in Tokyo, you get the Asia Edge. This is the backbone of services like AWS Route 53 and Cloudflare, ensuring user hits the server with the lowest possible latency. When it comes to high availability, DNS is your first line of defense. DNS providers perform constant health checks. If an IP fails, the provider dynamically and automatically pulls that dead IP from the authoritative responses. But there is a massive dependency here. DNS level failover is useless without ultra low TTLs. If your TTL is set to an hour and your server catches fire, your users will be trying to reach a dead IP for the next 60 minutes. To achieve true high availability, you need your TTL in the 60 to 120 second range. DNS was designed in the 80s for a trusted academic network using unencrypted unsigned UDP. In 2008, Dan Kaminsky discovered a massive exploit, cache poisoning. Because DNS didn't require a handshake, an attacker could flood a resolver with the forged responses. If, it, if they guessed the transaction ID correctly, the resolver could cache the fake IP. The result? Every single user on that resolver, potentially an entire city, would be silently redirected to a malicious server. This failure cascade proved that trust is not a security strategy. To fix these vulnerabilities, we developed the Armor, DNSSEC, DOT, and DOH. DNSSEC adds cryptographic signature to ensure integrity. It proves the record hasn't been tampered with, though it doesn't hide the data. DNS over TLS, that is DOT, wraps a query in encryption on port 853, but it is easily blocked by firewalls. DNS over HTTPS, that's DOH, is the modern standard, hiding DNS traffic inside standard web traffic on port 443. This makes it incredibly resistant to surveillance and filtering, ensuring your queries stay private and secure. Caching isn't just for successful lookups. We also need negative caching. When a malicious client floods a resolver with requests for domains that don't exist, like fake-1.com or fake-2.com, it can overwhelm the authoritative server. To prevent this, resolvers cache the annex domain result. A key distinction for production. Annex domain means the domain itself doesn't exist. No answer means the domain exists, but it doesn't have the specific record type you asked for. Caching these nodes is vital for protecting system resources during an amplification attack. And there we have it, the complete architecture. It's an elegant system that balances scale, speed, and trust through delegation, caching, and encryption. Now I have a question for you. Have you ever experienced a DNS nightmare during a production migration or a detailed misconfiguration? Share your stories in the comments below. I love to discuss them. If you found this dive helpful, please like, share, and subscribe to CSAI Think Tank Learn. Don't forget to check out the full article on our site. Thanks for watching, and I'll see you in the next layer on this stack. Thank you.